Welcome to the Explainer. Right now, we're witnessing one of the absolute most fascinating divergences in modern tech, specifically the architectural paths of AI hardware. Today, we're completely moving past the basic AI 101 stuff. We are diving straight into the silicon, the raw physics, and the incredibly complex financial engineering required to actually sustain real-time AI. So let's get into it.
Okay, let's dive into this. 21 petabytes per second. Just let that number sink in for a second. That is the on-chip SRAM bandwidth of the Cerebras Wafer-Scale Engine. We're starting right out of the gate with this massive number because, well, it immediately establishes the extreme physical stakes of what we're looking at today. It's an order of magnitude that literally redefines how fast data can move when it never actually has to leave the silicon.
So, here is our analytical roadmap for today. We're going to cover the AI paradigm shift, breaking the reticle limit, what we're calling the Ferrari versus bus showdown, software-hardware co-design, and finally, extreme infrastructure economics.
All right, starting off with Section 1, the AI paradigm shift, and specifically, the interactivity premium. You know, the market's willingness to pay has fundamentally shifted lately. It isn't just about raw intelligence anymore. It is all about extreme interactivity. Just think about the frustration of waiting for an AI to generate a response. If that AI pauses, your flow state just breaks, right? Because of this, fast tokens command a massive premium. We're talking up to 6 times the price for just 2.5 times the speed. This intense demand for zero-friction AI is currently capturing roughly 80% of all AI spend. And to sustain that, the industry is quickly realizing that a completely new physical architecture might be required.
Which brings us to Section 2, breaking the reticle limit and escaping 2D constraints.
So, the crucial point here is that the dreaded memory wall in AI, it's fundamentally a physics and manufacturing problem. See, chip makers are bound by what's called the reticle limit. It's a strict lithographic boundary that basically caps a single piece of silicon at typically 858 square millimeters. And because you literally cannot make the monolithic chip any bigger, you're forced to pipe data off the chip to external memory. And naturally, that creates immense bottlenecks and latency. But here is how Cerebras completely shatters that physical law. Instead of chopping a standard 300mm wafer into hundreds of tiny, reticle-limited chips, they just keep the entire wafer intact. Imagine keeping the entire pizza instead of just taking a single slice. The result is this massive 46,225 square millimeter silicon square. By bypassing that limit completely, they can cram 44 gigabytes of memory directly onto the chip itself. The data lives exactly where the compute happens. No trips off-board required.
Now, you might be wondering, how on earth is a single chip that massive actually economically viable? With a traditional wafer, if there's even a microscopic flaw, you just throw away that one small ruined chip. But if there's a flaw on a massive wafer-scale chip, well, you obviously can't throw out the whole thing. So the architecture relies on what is known as yield harvesting. They map the wafer, find the microscopic defects, and then dynamically route around those broken cores digitally. It essentially absorbs the defects to achieve a near 100% system-level yield rather than just tossing out flawed silicon.
Let's move to Section 3, the Ferrari versus bus showdown, looking at architectural divergence.
Think of it like this. It's basically the Ferrari versus the bus. The Ferrari, that's Cerebras, focuses strictly on zero-latency on-chip SRAM memory. It is highly optimized for single-user extreme speed. The bus, on the other hand, representing traditional NVIDIA architecture, relies on high throughput, massive batching, and external HBM memory. The bus is great because it can move thousands of concurrent users all at once, but it comes with higher latency per token. The Ferrari, it moves one user at blistering, absolutely unmatchable speeds. And this brilliantly illustrates exactly why that performance gap exists in the first place: physical distance. Cerebras completely eliminates the physical distance penalty because the data simply does not have to travel over external wires, period. Conversely, traditional architectures are severely bottlenecked by unavoidable off-chip trace latency. You just can't beat the speed of light, and physically moving data across a motherboard takes precious time. The brutal math of inference decode makes this incredibly clear. Traditional GPUs essentially starve for data during batch 1 processing. Their massive compute engines just sit there, idle, waiting for external memory fetches. But Cerebras, because of that insane 21 petabytes per second of internal bandwidth we talked about earlier, it guarantees 100% utilization of its arithmetic logic units, the actual math crunchers, without a single idle cycle during batch 1 decode.
Moving right along to Section 4, Software-Hardware Co-Design and the Compression Imperative.
So here's the catch. You have a very strict hardware constraint, a 44GB SRAM hard limit on the wafer. You can't just stream data in from the outside without completely ruining your speed advantage. Therefore, engineers are practically forced into aggressive model distillation. They have to take a multi-trillion parameter monolithic model and just crush it, compressing it by over 10 times down into a highly dense 120 billion parameter target. This is done so the entire model can live natively on the die, which completely neutralizes that external I/O bottleneck.
Now, what's really interesting about this is that it introduces an architectural paradox known as the stranded silicon effect, or the island problem. Think about the perimeter of the wafer. You've got this massive, high-speed core, but it is essentially trapped by a severe networking choke point, just 150 gigabytes per second at its shoreline. So you have immense speed inside, but piping data off the edge of that physical circle forces incredibly complex pipeline parallelism if your model happens to exceed that 44 gigabyte threshold.
Finally, let's dive into Section 5, Extreme Infrastructure Economics and the true cost of all this.
The physical reality of actually running this hardware is pretty visceral. A standard high-density GPU rack requires roughly 1.5 liters per minute per kilowatt for cooling. The Cerebras system, it concentrates a staggering 25 kilowatts of heat onto a single wafer. Sustaining that demands massive 4.0 liters per minute extreme flow rates, plus a strict requirement for 5 degrees Celsius chilled water. You are essentially plumbing a commercial freezer directly onto a microchip. You absolutely cannot just drop this into a standard data center.
All of this builds into an intense engineering checklist for what experts are calling the neo-cloud architecture. To sustain that 25 kilowatts of power density, you need custom vertical power delivery that steps down 50 volts to exactly 1 volt perfectly. You need highly specialized fluid dynamics. And because of that edge bottleneck we just discussed, the physical facility architecture itself has to rigidly and perfectly mirror the silicon architecture. It's a massive undertaking. And all that brings us to the staggering economic reality, an estimated $450,000 bill of materials for a single rack. But honestly, what's most fascinating here is that the raw compute silicon, the giant wafer itself, is actually a surprisingly small percentage of that cost. The extreme infrastructure is what dictates the price. You're paying for custom engine block mechanics, specialized power modules, and mandatory memory offload nodes packed with thousands of dollars of external RAM, all just to compensate for the wafer's internal storage limits.
Naturally, pulling this off requires highly sophisticated financial engineering. When we look at the strategic partnership flows, we see exactly how this extreme hardware gets subsidized. Through mechanisms like operating loans and equity warrants, massive capital injections effectively subsidize this incredibly expensive, highly specialized infrastructure. It creates this intense strategic lock-in where CapEx burdens are reduced through equity swaps. This artificially inflates top-line backlogs and ensures a strict mutual dependence between the AI software layer and the custom silicon layer.
Which brings us to our final overarching question. We've seen the breathtaking physics of wafer-scale speed, and we've walked through the brutal, unavoidable realities of its deployment economics. Ultimately, will the market's demand for absolute, real-time interactivity justify a permanent divergence in how we build data centers? Or will these crushing physical infrastructure and cooling costs trap wafer-scale AI as a high alpha but highly specialized niche? It is a fascinating standoff between the laws of physics and the laws of economics. Keep this framework in mind as you watch the next generation of data centers come online.